Hi, in this video, I will do my best to guide you into developing a proper comprehension of what implication means, why it is defined the way it is, and more. But before that, I think that a proper introduction to this topic will be to first justify why we're going to do this, which is done when we answer this question. What is the importance of implication in the further study of logic in mathematics? The short answer will be to say that logic is the motor of mathematics or something like that. But this would only let us to question the reasons of why that statement is true. So in order to give a better answer, we need to understand more about logic and math. But first of all, as a kind of disclaimer, I have to say that there is no general definition of what logic or math is, such that the answer is universally accepted. But still, we're going to try to give an answer to understand more of the essence of both things. What is logic? A definition that I got from Wikipedia, it states that logic is the systematic study of valid rules of inference, where rules of inference are the relations that led us to the acceptance of one proposition on the basis of a set of other propositions. In the case of math, we're not going to exactly answer what is math, but we're going to answer what is done in math. So, well, part of the essence of what is done in math is that of establishing the truth of some propositions from the use of rigorous deductions based in other propositions, which belong to a particular axiomatic system. Now I think that the question of the introduction has been answered. But still, another reason why I believe that understanding and defining the implication is so important is because in the process of trying to figure out and understand tricky or difficult things like implications comes with the benefit of helping to develop your mathematical thinking, which is a valuable skill. But to be more explicit, implications are the means in which we prove and deduce stuff in mathematics. That's why implications are so important. So, if we want to implement rigor to these deductions, then these deductions have to meet certain parameters. One of the most important is that of being unambiguous. Therefore, the language in which we make deductions and the way we define implication itself must be unambiguous. Hence, we will use a language that has a property and that will also let us talk about the truth of propositions. This language, as you might have guessed, is called propositional logic. In this language or system, the most basic elements are propositions, which can be used to form new propositions from some basic operations. The first three basic operations that we will see come from formalizing the conjunction, the disjunction, and the negation. And I want to stop a moment and talk a little about disjunction because there are two types of it. What I want to say is that when we say a statement like P or Q, we are sure that it is a disjunction, right? But it can be an inclusive one or an exclusive one. We say that P or Q is an inclusive disjunction when either P is true or Q is true or both are true. And we say that P or Q is an exclusive disjunction when either P is true or Q is true, but not both of them at the same time. So that's basically it. In these tables, which are known as truth tables, are shown all the possible combinations that these operations can have individually. And basically, these truth tables define the way we use the conjunction, the disjunction, and the negation in propositional logic. When we have the statement that P and Q is true, then we have that P has to be true and Q has to be true. In every other case, P and Q is false. For the case of when we say that P or Q is true, then we have that at least one one of the components of the statement P or Q has to be true. What I want to say is that either P is true or Q is true, or both of them are true, right? That's what I said before. And with negation, basically negation, what it does is that it swaps the truth value of the original statement. For example, if we have that P is a true statement, then not P will be a false statement. If we have that the original statement P is false, then the negation of that statement, or not P, will be true. Now we can start talking more about implication and try to define it as an operation in the language of propositional logic. In other words, we're going to define the truth of an implication from the truth of his components. But this is no easy task, as we may see with later examples. But before showing some examples, let's first get more in touch with implication. An implication is a proposition, which in its most simple form is composed of two propositions. One is called antecedent and the other is called consequent. Here we have two examples of implications, where the words painted in red are the antecedents and the words painted in blue are the consequents. A property of implication that will be of big help in our task is one that I called as a property of genuine implication. And to be more precise about what I mean with the words if and only if, I will leave the definition of what I mean with the words if and only if. And also another property that I want to talk about is this one. This proposition may seem very trivial, and it is. But what I really want to say with this proposition is that there can be cases where P implies Q is not a genuine implication, but still, it is a true proposition. An example of this is when we make use of the principle of explosion, which says that whenever a contradiction is true, then any statement can be proved. We will get more in detail about the principle of explosion later in the video. But now let's continue and see two examples of implication and see if they are true examples, they are true implications. The first one is obviously true, but the second one isn't, even if the antecedent and the consequent are true. And this is because the truth of the antecedent is not responsible at all for the truth of the consequent. Here we find a difficulty that did not appear in things such as conjunction or disjunction. And it's the fact that when we say P implies Q, we say more than just something about the truth values of P and Q, but we also affirm the existence of some kind of causal relationship between P and Q. What I mean is that it's not enough to talk about the truth values of P and Q in order to determine if P implies Q, but also to examine whether P and Q have or not a causal relationship, if I may say it like that. So we can conclude that an implication can be broken down into two parts, a causality part and a veracity part. And to talk of the veracity of an implication when there is no causality between the components, it can be a completely nonsense, as we saw with the second example. So if we still want to define the veracity of an implication and still aim for an ambiguity, then we have to make sure that at least our definition behaves well whenever there is a genuine implication, because these are the cases in which we are ultimately interested. So let's define then a new operation that will be represented with an arrow like this, and his name will be conditional. This symbol right here, it's read like P conditional Q, and this will represent the truth of the implication if P then Q. In order to do this, the conditional will be defined such that has the next properties. P conditional Q is true if P implies Q, and P conditional Q is false if P not implies Q, or P does not implies Q, or P doesn't implies Q, however you like to say it. And the second property is that this definition can cause contradictions. So now let's analyze and define the truth of the conditional for each row of his truth table. But from now on, I won't say out loud or neither talk about the proofs that I will present unless there is something that I think that it needs to be clarified. The reason of this is to not make this video longer than it has to be. With that being said, let's start with the first row of the truth table of the conditional. In this proof, I want to talk about how we go from the third step to the conclusion. And for that, let's remember that we define the conditional by the truth values of its components. So if P conditional Q is true and both of its components are true, then we conclude that if P is true and Q is true, then P conditional Q is true. In this proof, what we have proved until the fourth step is that it can be the case that P implies Q is true whenever P is true and Q is false, because we will get into a contradiction. This means that P implies Q is false, basically, and therefore the negation of P implies Q has to be true. And from there, we can deduce easily the other steps. So now, after doing this, we will start to define the truth value of the conditional for when the antecedent is false. Here, things will start to get trickier because you may not have any intuition of what the truth value should be. After all, we only care about making deductions from true premises. And one can even think that the truth value in these cases should be undefined. But sadly, this wouldn't be a good definition if we aim for unambiguity. Hence, it's absolutely necessary to determine what the truth value of the conditional should be in the third and fourth row. But before starting with this process, I would like to give two hints that will serve us in our task, and I name these hints as properties of implications, and you can read them here. And if it's not clear yet why these properties are true, I will recommend to pause the video and think about them. After that, I hope that this will seem more intuitive. But still, I will prove these properties. So let's start with the first one. This proof is based on the fact that when we say that P implies Q, we're not saying only P implies Q. Also, I will leave here a particular and more concrete example. Now, let's continue with the fourth row of the truth table of the conditional. In this proof, I want to talk about how we go from the fourth step to the conclusion. And for that, let's analyze that not Q conditional not P is true when P is true and Q is true. This means that the conditional is true whenever both of his components are false, because not Q is false and not P is false. And from that, we can deduce that the conditional is true in the fourth row of his truth table. Having finished the process of defining the conditional, I think it will be a good idea to do a review of what we have done. Based on the property number 1 of the conditional and the fact that P implies Q if and only if not Q implies not P, then we get that P conditional Q is true if and only if P implies Q, which is obviously a false statement unless we make explicit a consideration that we talked about before, and it's that about genuine implication. So now, as I said before, let's start with a review by examining if this statement right here behaves well or is true, more formally saying, for each row of the truth table. If P and Q are true, then our definition obviously behaves well. If P is true and Q is false, then P conditional Q and P implies Q are both false. Hence our definition still behaves well. But things get trickier when P is false. In the case of the truth of the conditional, if P is false, then P conditional Q is true. Hence, if we prove that P implies Q whenever P is false, then our definition will behave well for every possible truth value of P and Q. So I will show you a proof of this, a possible proof, which is based in the principle of explosion. If I'm honest, I'm not so sure if this proof is correct, because one of the hidden assumptions that is being used in this proof is that of being able to state that P is true and false at the same time, which is not a possible thing. But one can argue that it's justified because we reach to these assumptions from the use of valid rules of inference. Therefore, a bifurcation is generated here. Either you argue in favor of this proof or you argue against it. If one argues in favor of these proofs, then P conditional Q if and only if P implies Q is true whenever P is false. Therefore, P conditional Q if and only if P implies Q is true whenever there is a genuine implication. If one argues against these proofs, which is probably because of the fact of having to assume that a proposition is true and false at the same time, then we cannot assure that if P is false, then P conditional Q if and only if P implies Q is a true statement. But we don't need to assure that, since in this line of argument, if P is false, then P implies Q is not a genuine implication. Therefore, the statement P conditional Q if and only if P implies Q is true whenever there is a genuine implication. But let's remember that P implies Q is a genuine implication if and only if it satisfies the condition that the truth of Q follows from the truth of P. But if P is false, in other words, P is never a true proposition, then this condition can be satisfied. Hence, an implication can be genuine if the antecedent is false. But in this line of argument, another problem arises, and it's to interpret what does the conditional means to be defined as true when the antecedent is false. My personal interpretation is that we define the conditional as true when the antecedent is false by two reasons: unambiguity and to avoid contradictions. The unambiguity part justifies why to even care to define the conditional or implication, as you may say it like that, when the antecedent is false. And to avoid contradiction parts justifies why we have to define it as true and not as false, basically, when the antecedent is false. And with this, I will finish the video. I hope that it was helpful. I personally recommend to ponder about each proof and argument showed in this video and ask yourself, is this true? How do I justify that this is true? Or how do I justify the contrary, that it's not true? These are the kind of questions that I think that will let you to comprehend almost any topic in math, or at least it will guide you in that path. So I will also appreciate any kind of feedback that you have because this is my first video. So goodbye and thanks for watching until the end.